Imagine you're training a neural network, and instead of feeding it thousands of images, you give it just one. But that one is so rich in detail, it teaches the model everything it needs to know. That's the power of diffusion models, and here's how they actually work. At their core, diffusion models learn to reverse a process. They start by slowly adding noise to data, say, a photo, until it's just random pixels. This is the forward process. But the magic happens in the reverse process. The model learns to gradually remove that noise, step by step, to reconstruct the original image from pure noise. Now, here's the deep technical kicker. Instead of training the model to predict the entire image at once, which would be impossible, it learns to predict just the tiny amount of noise added at each step. This is done using a noise prediction network, typically a UNet architecture which takes a noisy image and the current noise level, encoded as a timestep, and outputs a noise estimate. The model trains by being shown pairs of noisy images and their corresponding noise, learning to minimize the difference between its prediction and the actual noise. Over time, it becomes incredibly precise at denoising, even from completely random input. And because this process is stochastic, meaning it involves randomness, each generation can be different even with the same seed. That's why you get such diverse, creative outputs. But here's the real breakthrough. Diffusion models don't just generate images. They become the foundation for text-to-image, video generation, and even 3D modeling. They're not just tools, they're learning engines that understand the underlying structure of data. So next time you see a stunning AI-generated image, remember, it wasn't created in one step. It was born from thousands of tiny, precise denoising steps, one noise layer at a time. That's the quiet revolution of diffusion.